that
Mm-hmm.
I had with Udbhav while explaining grounding.
Mm-hmm.
Okay, so I'll go to the starting of grounding. Okay,
Mm-hmm.
so we know that in a monomer, typically you have, where is your like acoustic branch starts from zero,
Mm-hmm.
right? So what happens? Also, like just this thing is that here q is equal to zero means it is in phase, and q is equal to pi by a means it is out of phase, right?
Mm-hmm.
So your brilliant zone is basically a portrayal of in phase behavior to out of phase behavior. It covers everything, completely in phase, completely out of phase. When q is equal to pi by the if the unit cell I is moving, let's say in the right, then unit cell I plus 1 will move exactly same amount to the left,
Mm-hmm.
right? Completely out of phase. Okay. So when a monomer chain is completely in phase, the it interside potential, as you can say, the spring stiffness, they are not activated. So that
Mm-hmm.
is why the frequency is zero here,
Mm-hmm.
right? What happens
So
when
where the frequency is zero in the starting, right?
in the starting? The out
Mm-hmm.
of phase mode starts from zero frequency because interside potential is not activated when it is completely in phase,
Means
right?
it moves like a rigid body, right?
Yes, yes, it moves like a rigid body.
Mm-hmm.
So what we were discussing in the last class was if you have some grounding, then what happens is if you cannot have the rigid body motion because every unit
Yeah.
cell is connected to some grounding stiffness. But it's just a stiffness, it does not increase the degrees of freedom. So if you plot the effect, like this is the calculation for it. So at q is equal to 0 and at q is equal to pi by a. So if you see at both places you have a sort of plus kg by m term added here as well as here, right?
Right, right.
So at q is equal to 0, like here, omega should be 0 for the acoustic mode normally,
Mm.
right? But when you
Mhm.
have grounding, what happens
It's on.
is
Mm-hmm.
the spring stiffness kg, the grounding stiffness kg is k grounding, that starts acting, and then the when the entire chain is moving to the left or to the right, then you have this effect of grounding,
Mm-hmm.
right? And in both totally in phase and totally out of phase, both modes, right? So what we observe when you have grounding is that both, like the entire chain is sort of lifted up by under root kg by m, right? Hello.
Ah, yes, yes. I'm listening. I'm just muted. Yes, yes.
Okay, right. So now the question is, I think I'll sort of also like it's the same question to you. Sort of, can you hear me?
Yes, yes.
Yeah, so the question is, you know that there is something called a Bragg gap.
Yeah.
Okay. When does Bragg gap open? At Q is equal to pi by A. Why Q is equal to pi by A? Because that is completely out of phase. And that is where your lambda is equal to 2a. That condition, the Bragg condition is satisfied. So, because the Bragg condition is satisfied at q is equal to pi by a, we observe a Bragg gap, right?
Yeah.
Okay, so this is established so far. And then if you have a local resonator, then around the resonating frequency, say here somewhere, you notice that a band gap opens because the resonating frequency tends to absorb all the vibrations away from the main chain, right? So we know two types of band gaps. Now the question is, what is the type of band gap in grounding? This band gap here, what is it? Is it Bragg? Is it local resonance? Or is it something else?
It's local resonance, right?
Why do you say so?
Good morning, sir.
Hey, Bob. Okay. So that's an interesting question, right? Saurabh, Saurabh,
Hello, hello. Yeah.
Saurabh.
Hello, hello, hello.
Yeah.
Okay. So
So,
am I audible?
yeah, yeah, you're audible. You want to say or
Yeah, you can
pass
go
it
ahead.
on? Okay. So, so the answer is local resonance, but at a limit. What is the limit? Let's say you have a mass in mass system as shown here. And if the internal mass becomes bulkier, the resonating, like if M, capital M becomes infinity, then the resonating frequency goes to zero. But we also know that if capital M becomes infinity, the coupling strength M by M also goes to infinity, right? So when coupling strength goes to infinity, we know that the band becomes broader and broader. But the but when the resonating frequency goes to zero, we know the band becomes narrower and narrower. So this is sort of a game of zero into infinity, that type of a limit. So so that means grounding is basically local resonance based. At the limit, m is equal to infinity. Because if m is infinity, essentially it's like astronomical size, then it can be considered grounded. Does that make sense? Hey Krishna. Krishna, you're not audible. Guys, I think there is some technical issue. So anyway, we'll go ahead. Okay. So and the next thing that we discussed was what happens. We know that if you have a local resonance uh, band gap, so we saw the lower limit of the local resonance band gap. But let's see the upper limit. So we know that it opens like this. And if you increase, say this is omega naught. If you increase omega naught, then what happens is, go somewhere here. So if you further increase omega naught, essentially omega naught is tending to infinity. Then this line, which is omega naught, that tends to infinity. You're just left with this. So that means a locally resonant system, which is 2 degree of freedom, when omega naught tends to infinity, becomes monomer, which is a 1 degree of freedom system. And then this cutoff is, let's say, you have this. So if you make k tends to infinity, then essentially this is just one single rigid plus m. So now it's a monomer. So what we see is that locally resonant band gap, when m tends to infinity, becomes a grounded system, and when k tends to infinity, it becomes a monomer, a Bragg based, upper cutoff based band gap. Okay, so in this yeah, any if people have any questions, then I'm open to answering those. In the last class, we covered locally resonant systems, grounded systems, then we covered stiffness dimer, mass dimers. Yeah, we even covered long range interactions. I think Krishna presented his paper. Then, yeah, so we started from dimers. Before that, we covered Bragg scattering monomers. So if people have anything so far in the discrete, uh, any discussion they would like to have, then I'm open to it. It seems like people are have so far understood everything and are thinking about things. So we'll move on to the next topics. So the next topics are, so these are some interesting topics. We have something called LLR. So what is an LLR? LLR is lateral local resonance. How is it different from local resonance? We'll have a look. And then these are next topics. And then we'll have IA, that is inertial amplification. And then, so we'll understand that inertial amplification is a design which is based on a mechanical element called inerter. An inerter is incorporated into a unit cell. So we obtain inertial amplification in a metamaterial. Uh, that's what it is, like ability to use inverters inside architected structures. And then we will have a MATLAB session, coding session, where we'll see how to plot various dispersion curves. We'll see how to plot attenuation curves. We'll see how to plot finite chain, the eigenvalues, and eigenvalue analysis of finite chains. So we'll see these, and in later lectures, we'll also cover um effective mass, which is dynamic mass. Then we'll cover effective stiffness, and we'll see uh, what are the effects, or like how do you get effective mass, how do you get effective stiffness, um, can we homogenize any unit cell uh, to find its effective mass and stiffness? Can we, yeah, so we'll do that, and then we'll see maybe effective properties in inertial amplification systems. Uh, how do they relate? What are inertial amplification systems? Is the type of band gap, again, is it same as Bragg? Is it locally resonant? Or is it something else? Or like how we saw grounded systems, is it some limit of something else? So we'll have a look at those as well. Uh, and then we'll cover uh, low frequency systems. So before that, we'll cover band gap quantification measurements, various types of them, and uh, we'll have a comparative analysis. Then we'll also see what is the long wavelength wave speed. So that means that what is the wave speed? Yeah, before covering wave speed, I think I should cover group velocity and phase velocity as well. So yeah, I'll cover group velocity and phase velocity. Then I'll cover what do they mean, uh, how to interpret them in dispersion curves, and then we'll see how we will calculate various things, especially long wavelength, wave speed, and what is its relevance. Uh, so so that is like, just to give a hint, that is like continuum limit, uh, in a sense, like, so when you are zooming out a lot, and the wavelengths are much larger, then what is the behavior of the material? right? So you may have two materials behaving the same for very large wavelengths, but as the wavelengths become smaller and smaller and they start matching the dimensions of unit cells, you might see totally different behaviors. So that would be interesting. So these are the topics which will be covered so far. If anyone is particularly interested in any, I would like to know so that more focus can be laid on it. If nothing, then we'll take 5 minute break. Yeah, hi. So here's the paper. Um, Paper is titled Theoretical Investigation of Behavior of an Acoustic Metamaterial with Extreme Young's Modulus. Young's Modulus as in stiffness. So this later we'll find out that lateral local resonance that we're referring to, it's the same system that gives you negative effective stiffness, and the standard local resonance gives you negative effective mass. So, so look, it's a very foundational paper if you want to understand effective stiffness. Yeah. So, so this is the unit cell. So what they are showing is this is made of four rigid massless truss members. So these are massless and they are rigid. However, they are connected using a pin jointed system. So what what happens because of the pin jointed system is that you notice, yeah, you see that these pin joints, and this rigidity is really important. So basically, when this degree of freedom, this is u1, uh, let's say this is u1 of, let's say, I minus 1 or something. So when these independent degrees of freedom are moving, then these points which are indicated by v1 here, these are moving laterally, and the movement of these is totally dependent on the movement of these. So this is not an independent degree of freedom. So if these truss members, they were not rigid, then these would be independent degrees of freedom. So that rigidity is really, really important. Then comes the fact that there is a spring here, there is a mass. Right? So this K2 and M2 as seen here, yeah. So this is the local resonator, but it is attached laterally, like if this is the main direction, so this is like transverse or lateral direction. So and this mass is supposed to be constrained to move in only vertical direction. So if we analyze this system, now it's a very tricky system. At first, there are many things here, but it can really be simplified. Uh, so one thing is that how do we know the constraint, the kinematic constraint of how V1 moves when U, the U's are moving. So, so we have to take the length of each truss member to be constant. So when we take that, then we get a constraint, and through that we get this Yeah. So that constraint essentially helps us. Yeah, this constraint helps us. Okay, cool. And this is what it is written. So what is V1? Your equation. Um, yeah. We have a look at equation 3. What you'll notice is that V1 is related to U1 and L by D. L is basically the length of this truss along the main direction, and D is the lateral dimension of the truss. So L by D is an aspect ratio that is really, really important. And these truss-based systems are the backbone of, even later we'll see, inertially amplified systems. So they are heavily relying on these truss-based systems. So this is how V1 through equation 3 is constrained to move according to how U1 moves. So when that happens, so essentially you just have 2 degrees of freedom in this unit cell. One is of the main mass, which is at these points of U1, and one is this lateral local resonator, M2. These are the 2 degrees of freedom. Then there is no, it's like massless truss member. If there were mass there, uh, even then technically it would not be an added degree of freedom because the movement is still constrained. Because the mass matrix would become complicated. That's what we would notice. So this can be simplified to to the diagram, the simplistic diagram on the right, where sigma is equal to E effective into strain. So if we calculate, uh, you know, sorry, yeah, so equation 4 captures the force here required to vibrate at some omega, and omega naught is the local resonance frequency per this under root k2 by m2 basically. And if you substitute this, and if you divide by area and also you try to get stress, you get stress in this form. So it's essentially E effective by E naught. E naught is the static stress. You get it in this form. What is eta? Eta is operating frequency by resonator frequency. And what is mu? Mu is L by D square. Means L by D is the aspect ratio. So mu is the aspect ratio. Delta is the stiffness ratio, K2 by K1. Purely based on these ratios, you get an equation that tells you at what frequencies, because eta varies with frequencies, at what frequencies, what will be the effective stiffness. Anyway, uh, we'll, we'll touch upon this again, but the point is to understand that there is something called lateral local resonance, and that gives you effective negative stiffnesses. This is the paper, the foundational paper. I encourage everyone to have a look at this paper. Anyway, we'll dissect this paper a bit. Yeah. So you see, eta is that frequency ratio. When eta is approximately equal to 1, you see this uh, pattern of E effective. Suddenly, there's some sort of singularity here. So before and after, E goes to infinity. And there's a range of values where E is negative. This is negative. It is the whole unit cell and the chain. You can have a look. Yeah, so this is the, I think, the first subplot is the dispersion relation, where blue is the acoustic mode, red is the optical mode, the red dotted line, dashed line. Then second subplot is showing you attenuation. So we spoke about attenuation. What is attenuation? We wrote wave number q as alpha plus I beta. So I think they have also followed the same notation. Alpha is the real part of the wave number, and beta is the imaginary part of the wave number. So see that only in the band gap the imaginary parts of wave number exist. Everywhere else the imaginary part is zero. This is what attenuation means. Then further here alpha is equal to alpha is varying. As the band varies, alpha value varies. Right? And this last one is effective modulus calculated. The one interesting thing is there are two places where we observe singularities. One is this attenuation singularity, which is happening in the subplot B, the brown dashed line. Right? It is happening in somewhere in between 0.6, 0.8. That is the attenuation singularity. The other singularity that we notice is happening in subplot C at approximately 1. So what is that? What is this? They are not happening at the same frequency. So notice that the effective stiffness, which is plotted in C, when it goes to infinity, attenuation need not go to infinity. Whereas you see that when effective stiffness is going to 0 here, then we see that attenuation goes to infinity. So this is a different relationship than, let's just, you know what, since we have started covering this, let's just go to effective mass as well. The effective mass. Yeah, so this paper is on the negative effective mass. Again, this is also sort of a seminal paper. Um, Here they talk about in equation 2, they talk about effective mass. And you see that on the RHS, the equation, there is some denominator, and if that denominator becomes, you know, let's say, negative enough, then the overall value will also be negative. The denominator becomes 0. You see that M effective will hit singularity. So that singularity is, again, this is the mass, standard mass and mass. They have not connected it. They have not shown a connection, but it will not change the equations. Right. So they have plotted from minus pi to pi. So they have plotted the first Brillouin zone, not the irreducible Brillouin zone. And we see that they follow the same notation. Blue is the acoustic mode, red is the optical mode. This is the dispersion curve. Further, here, note that typically in dispersion curves, your frequency is on the y-axis. Here, they are showing the frequency on the x-axis. And alpha, again, Q is split into two parts, alpha plus I beta. Yeah. So what we see here is that alpha values, they are the real part of the wave number. Beta values, they are the imaginary part. So in the band gap region, which is from 1 to 3, see that when here it must be 1 to 3, although the scaling is such that we cannot tell. In the band gap region, the alpha values can be anything, but beta values are non-zero. So that's just the attenuation in the band gap. If we look at the effective mass, we see that the singularity in effective mass also happens at 1. The singularity in attenuation also happens at 1. This is in contrast to here, which is the effective stiffness. Remember, lateral local resonance gives you effective stiffness. Local resonance gives you effective mass. Right? So here we see that the singularities in effective stiffness and singularity in attenuation, they do not happen at the same place. So this is going to be really important later on, which we'll cover. And they say that you could use something like this, some possible design where these are acting like trusses, and then these are acting like resonators. This is a base material in green, and somehow it will attenuate. And this is just an idea, not gone too much, I think, into. Yeah, they've not gone much into implementing it. However, yeah. So let's get back into our paper, our work. Okay. Each unit cell has a truss mechanism. Members of the truss are all of length L, forming a rhombus. And let's say that rhombus, and yeah, this is L. This is D. If you here, let's say like if L is greater than D, then yeah, then you get something like this. Right? So it's a rhombus mechanism. Although this is a non-linear mechanism. However, we linearize it. So now let's say linearize it. So let's say this is u of I. So this is u of I plus 1. We try to derive the equations. So this is u of I, this is u of I plus 1. And let's say this is v of I. This is this some this is actually just this will be the mean of u of I and u of I plus 1. So it's not an independent degree of freedom. I mean, it's easy to write. So you get something like this into right. So this is the linearization. How do we get this? We're assuming that the length L is constant. Something like this. So if ui moves like this, then what is the movement of vi? Okay. do the calculations for the truss. To draw a free body diagram. Or something like this. And let's say there's let's say the trusses are carrying tension. Okay, T. So this is T1, this is T2. We can T3, T4. So if the trusses are tensile, then this point is being pulled by T1. This point is being pulled here by T1. Immediately. Okay. Further, we know that maybe the adjacent unit, so there's a mass here, right? Okay. Okay. And there's a mass here. There's a spring here that pulls it by K. Is it K? So the spring force is accounted for. The tensile forces are there, right? And then there will be one force here that will be because of K2 spring, but K2 spring. So this is, let's say, V2. If that is V2, then K2 into V2 of I minus V1 of I. Okay, I hope it's clear so far. So now what we do is, so the net force at this point has to be 0. Yeah. Yeah. So this is theta, and this is 90 minus theta. What is theta? Theta is tan of theta is equal to d by L. It's actually d by 2 by L by 2, but we can ignore, we can cancel the by 2. So tan theta is equal to d by L. Okay. So at this point, balancing the forces in y, we get is T. Also, using symmetry, we can say that T1 is equal to T3 and T2 is equal to T4. Yeah. Then further, T1 plus T2 into cos of 90 minus theta is equal to A2 V2 minus V1. So, a force balance at the top of the truss, that point. That point does not have any mass, so F is not like, yeah, F is equal to ma, like m is 0, so it's just force balance. Okay, then yeah, further what we can do is we can substitute what is V1, V, V1I, right? T1 plus T2 sine theta is equal to K2 V2 L by 2D into U of I plus 1 minus U of I. Yeah, makes sense. Then if we Yeah. So welcome back. We're having this. What we see here is, yeah, so far we have written the equation here. So let's write the force balance for M2 in y direction. Okay, this is x, 0y. So free body diagram of M2. V2 minus V1. However, as we have already seen, minus V1 can be written as in that case if we write mhm, then what else can we write? So we assume that this mass is being pulled like this, then we can write the equation for m in x direction. As we see that T1 is equal to T3, the component of T1 in x will be T1 cos theta. So it will be T1 cos theta Oh, also, I think we forgot to write. We can also do force balance at this point in x direction. We forgot that. So that would be T1 plus T2. That would mean T1 equal to T2. And we know that T1 and T3 are same. So essentially all the T's are same. Yeah, so the conclusion is T1 equal to T4 is equal to T. Okay. Yeah, we had missed this. Then, yeah, so further what we get is, so this, you can call it T of, let's say, I. Okay. So this will be T of I. This will be T of I. T of I minus 1, right? So what do we have here? We take the components in X, we have to take the cos theta components. Then further, we can write this equation as 2Ti is equal to RHS by sine theta, right? So this is your equation A. A, we have 2Ti is equal to K2 V2I plus L by 2D U of I plus minus U of I by sin theta. This this is B, let's say. Okay, then this is 1. Then substitute D in 1. So this 2Ti can be substituted. This 2Ti can be substituted. And then we'll have cos theta by sin theta. 1 by tan theta. 1 by tan theta we can write as L by D. So overall that becomes L by D K2 V2 I plus L by 2D U of I plus U of I minus L by D K2 V of 2 I minus 1 plus L by 2D U of I minus U of I minus 1. Minus K U of I minus U of I minus 1 equal to M U I. Brilliant. Now we have to simplify this. Hello. Yeah. Okay. We take this common. Then okay, these two terms are dealt with. Right now we combine this and this. So we have to take as half L by D square K2 is common. I think yeah that works. So Yeah, the U terms are sorted. Looks like, yeah. Now if you look at the V terms, these two. Yeah, it's fairly simple. V2 of I minus V2 of I minus 1 L by D K2. Yeah. So that's one equation for sure. The other equation has to be this one. So we need to combine these two equations. U, then V2, think. Mass matrix looks simple enough. Yeah, this looks simple. Now plus, let's have a look at the stiffness matrix. It will be a 2 here. It will be 1 minus cos QA. 1 minus seems to be some error here. Okay, no, it's fine. Yep, it is here. That's what I was wondering. This is the equation. Yeah, so finally we combine it. We'll get the dispersion relation. Okay, so let's try to write. Remove this 2 here and we can multiply this by 2. Yeah. Okay, so this is the determinant is equal to 0. That will give us the equation. Okay, so now what will that look like? Just like the local resonance case. However, there will be two, two frequencies of worth noting. One frequency is when we have effective K tends to infinity. One frequency we have attenuation beta tends to infinity. They are not the same. We see that typically this is broader than local resonance for the same frequency. We notice that typically when the frequencies are lower, we see that the band gap reduces. So we'll see the same thing here. However, because of this truss mechanism, it is broader. And there's an additional parameter of L by D here. This L by D. See this everywhere. So that parameter gives us a lot of cumulativity in your local resonance. Particularly if you increase L by D, you can hit lower frequencies. So that is the lateral local resonance. Although it's a bit complex compared to local resonance, there are certain criticisms of lateral local resonance. One is that there are lots of idealizations. There's a reason actually that lateral local resonance is not easily achieved. In fact, you could, you could say that there are no studies which have 100% been able to demonstrate this theoretical phenomenon. You can get negative effective stiffness, but this exact system you cannot get. And there are certain reasons for it. One reason is that these thicknesses here, they just seem to be dangling. And yeah, they're just dangling there. So when most of the truss is moving here, let's say in the horizontal direction, we say that the stiffnesses are constrained in Y. But in reality, the way these equations have been considered in this paper, if M2 is constrained to Y-axis, but let's say this point moves, then the spring K2 will elongate. The spring will elongate. That will produce certain forces. So that has not been modeled in this. So in a way, it's assumed that if the point, the top of the truss, if it moves horizontally, we assume that M2 also moves with it horizontally somehow. But at the same time, we also we're not considering any horizontal inertias of M2, nor are we considering any uh, stiffness forces due to the stiffness elements in the horizontal direction because of K2. So it's really you see there are certain deficiencies in this model per se. However, uh, but what this model shows, uh, it hits the jackpot in capturing effective modulus. So that is why this model is also a bit complicated. There are multiple assumptions and uh, lots of trusses. We are assuming rigid yet massless. But to be honest, it's not possible to get massless uh, trusses. We could make them close to massless in comparison to other masses. But yeah, you see, there are fundamentally a lot of assumptions in this model, and yeah, we'll nonetheless, this is since this is like a pioneering work, we still covered it, and we'll plot this model in uh, MATLAB. So next we will go to inertial amplification. Before going to inertial amplification, uh, yeah, I can show some results, but let's just try this sake. So we'll take a break. We'll take a short 2-minute break.
Shrikant, you're muted.
Yeah, bro.
Hmm?
Yeah, what's up?
Yeah, yeah. Go ahead.
So you have awesome. Nice to be having you. So I'll give you a recap of lateral local resonance. Or do you want to start with inertial amplification?
Mm, up to you. You can start with the inertial amplification.
Really? I thought there was something interesting here.
No, but like, sure.
Good. So, so yeah. See, lateral local resonance. I'll show you. So this is the unit cell, and these are the trusses, and they are pin jointed, and there's a uh, local resonator which is connected laterally, sort of. And then we show that this rhombus mechanism, like it can. So this is a squarish rhombus, and then this is an elongated rhombus, and it's a mechanism. Uh, so it doesn't add any extra degrees of freedom on its own. Right? So overall, this will be a 2 degree of freedom system. So, and then if you try to see how will this point, the top of the truss, move, you will realize that um, it will depend on how of course, the two horizontal points are moving, and the rigidity is very very important here because that is what reduces gives you the extra constraint of length L being constant. So at the bottom left, you see a wall and sort of a floor. There's a rod of length L. I think this problem was there in JE somewhere. Like, how does one point move when the other moves, given that the length is constant? So it's the same problem. So you find the relation between V and U, and then you linearize it, and this is what you get ultimately. Right, and okay, so this is just the basics. And then we assume certain tension inside the trusses. Uh, we assume that these trusses they are not carrying any. Uh, they're only carrying tensile or compressive force. They don't have any shear or bending. Um, Now, why is that? Because they are connected through pin jointed mechanisms. Right. So yeah, some of the assumptions I think it's important to highlight, for inertial amplification. So yeah, only tensile, compressive forces in truss elements is the consequence of pin jointed. Let's say if you remove the pin jointed, or let's say additionally if you add some, rotational stiffness or something, then there would be shear and bending, and those things would be really crucial. Or if this uh, beam was not straight, if it was curved in some way, then the point of action. So then you'd again see some sort of shear or bending moment because it is straight and it's pin jointed. So it's like making it really really easy. Then we assume that they are massless. So I'm just listing out some of the assumptions that make this impractical and why we slowly go towards inertial amplification. So this is right, this is massless. Then further, Are you there with me, bro? Uddhav? Yeah. So anyway, I think Uddhav will have a look at the recordings. So this this mass M2, uh, although it can move, uh, uh, if we say that M2 is constrained in the vertical direction, then what happens is that if the lower point of the spring K2 moves, then the spring will get elongated. But we have not accounted for that. At the same time, if we say that M2 is free to move in the horizontal direction, then M2 would have some inertia. So neither the spring force nor the inertia uh, due to the horizontal movement of M2 is accounted for. So that makes it physically impossible, even from physics point of view. Say neither inertia or inertia of M2 or stiffness of K2 in the x direction is considered. Right. So these all make it impractical system. These are assumptions in lateral local resonance based systems. There are more assumptions, but yeah, I think these are the main ones. Those. Udbhav? Yeah, so these are the main assumptions. Okay, so um, let's move to inertial amplification. So, what is inertial amplification? So let's, before going into inertial amplification, let's understand what is the need for inertial amplification. Right? Right? So, okay. Yeah. So what is this graph? So this graph is showing that the this is the band gap. The blue and the reds are band gaps. But this is the variation of band gap as the resonator frequencies are varied. Right? So when the resonator frequency is, let's say, 1, then in the lateral local resonance we see band gap somewhere here. In the local resonance we see somewhere here. The resonator frequency is 1.5, we see something like this. Obviously, since the resonator frequency is increased, we see that the band gaps go higher and broader. Similarly, when the resonator frequency is decreased, um, then we see that the band gaps they get narrower. Yeah, sorry for that. So as the resonator frequency goes narrow, then it goes low. That means if you were to obtain low frequency band gaps, but you want them to be broad, how do you do it? So, so the aim of obtaining low yet broad band gaps is what drives the research in this direction, in this area. So another thing, yeah, maybe I'll cover that later. So next up is inertial amplification, right? So what is inertial amplification? Essentially, yeah, inertial amplification is based on something called inerters. So this is an inerter. What does it do? It can have differential acceleration at its ends. So here we see U1 double dot, here we see U2 double dot, and B is the inertance, and F is the force applied. And what happens is when you apply a force, typically like Newton's laws of motion, F is equal to ma. So that m is the inertia, and right, so this is also in that form, F is equal to B delta U. So the inertia is stored when there is differential acceleration across its ends. Not like it is, it's still obeying Newton's laws. It's just written in a different way, and whatever is inside is a black box. So from the outside perspective, this is what happens. And so if you compare F is equal to ma and F is equal to B delta U, the idea is to have really high B by M. In the sense, a lot of inertia should be stored for differential accelerations for a given mass. So B by M, inertance by mass, that should be high. What happens if that is high is a lot of your kinetic energy, when it is stored in inertia, uh, yeah, so a lot of the kinetic energy when it is stored in uh, no, I think it's reverse. When potential energy is stored in kinetic form, there's an inertia term there, If inertia is high, then the movements are lower. So inerters are typically also used in vehicle suspensions and things like that. But what are we doing here? Here we are trying to incorporate that inside a unit cell. So this is again a very important paper. We'll cover this. So inerter-based metamaterials. So the idea here is incorporate, like they have shown, inerter inside the unit cell. This red dotted line is the unit cell. That box is the unit cell, and yeah, yeah. And then what really happens is, let's say broadly, if you try to understand, if you have a uh, let's say when you have out of phase modes at Q is equal to pi by A, which is at the end of the brilliant zone. At the end of the brilliant zone, when you have that out of phase mode, and if you incorporate an inverter, that out of phase, can be, it plays the role of delta U in the inverter, and then effectively the inertia of the mode is increased. What happens when inertia of the mode is increased is that the modal frequency goes down. That is what is targeted, is that if the lower cutoff of a band gap goes down, then the band gap is becoming lower and broader. That is what inertial amplification tries to do. Okay. Now I'll share some papers uh, in inertial amplification. We'll try to understand where inertial amplification comes from. Let me share those papers. So there's a lot of work done by this guy called Yilmaz, Setin Yilmaz. I think he started this use of inerters inside the unit cells. I think this was his PhD work. Let me share. Utpav, you are there? Yeah. So, okay. So, analysis and design of passive band stop. By band stop, they just mean band gap. You can also call it stop band. Band stop filter type. Vibration isolators for low frequency applications. Okay. Okay. Now let's say you consider a typical base excited structure, right? This is your base. I think here y and x are different from, I think we had taken the base as x and the load as y. Here it's reverse. Anyway, so, and yeah, if this is the extra attachment. If this was not there, I think the pointer is not visible. Okay. If this dark colored MA and KA, that attachment was not there. So we call that dynamic vibration absorber. If that was not there, that would be a typical 1 degree of freedom base excited structure. And then we know that there is a resonance frequency. The resonance frequency would be at under root small k by small m. However, now what they have done is they have added something else here. So the mode shapes and they'll change. And see if there's a plot that depicts this. So transmissibility. Okay, the solid line is the added spring mass resonator system, the DV, dynamic vibration absorber. And dotted line is the single degree of freedom mass spring. So what is happening is that this peak is still there. This peak has not changed. Instead, we get another peak here and a dip. So yeah, we get an extra peak apart from the original peak. So it doesn't really seem that interesting. So we couldn't do anything regarding the peak. And yeah, we got extra degree of freedom for no use. Now, if you were to, so this is the concept of using lever arms. So what is this if you think about it? This is the load, right? This is the stiffness. Now, the load is resting on some seesaw kinematic mechanism. When the load goes up and down, the seesaw makes sure that the mass MIS here, that is shown by the displacement Z. So Z is linked to X, right? So I think there must be some equation somewhere about the linking of Z. Yeah, this is the equation. So Z is linked to X. Yeah. So the idea is you should maximize Z for a given X. How do you do that? Maybe you increase alpha here. What is alpha? Is L1 by L2. What is L1? This by this. Okay, so basically if you make the seesaw end of M isolator mass longer because of lever arm action, you have increased Z, and when you have increased Z, what is happening is although your X moves, let's say, but something, Z is moving violently at the same frequency, but a lot. So the overall inertia, uh, the overall inertia of the mechanism is really high. So what really happens is the peak associated with a single degree of freedom system that that will shift. Let's see if they have plotted. Uh, yep, yeah. So this was the single degree of freedom spring mass system, the dashed line. Then because of this lever arm mechanism, that frequency it has shifted from 1 to something like 0.5, zero point 0.4. So that seems useful. That means that we can shift the frequency peaks maybe by using the same mass, but making sure that the mass vibrates at much higher, accelerations, and that will affect the frequency, and then the frequency will be down, and then that is what has been attempted here. Now, further, what they do, I'm really like dissecting this paper because this is the foundational paper for inertial amplification in metamaterials. They try slightly different configuration, and they try to compare which configuration is better, type 1, type 2. Right? But that's not the idea. The idea is that whatever is the lever arm which is best, like yeah, it should be selected. But the idea is to use the lever arms to influence the frequencies associated with mode shapes without changing the mode shapes themselves. That is crucial. Do not change the mode shapes. Be Yeah. So now this is, I think there are more degrees of freedom here, and it's just experimenting with the types of connections. Yeah, and fundamentally, that's what, and yeah, somewhere there they have tried finding, so they call this solid line of term design because there's a dip here. There's a really nice dip around 0.5 in transmissibility. So earlier there was that dip was not there, only peak was shifted. So yeah, they are really playing with transmission plots. See, now they have compared, they show a really broad dip in the solid line. So that is what is the that dip in transmissibility is that is gonna, when you use something like that in a unit cell, that is gonna give you that broad band gap. Again, they're playing with the dips. Yeah. So this is the paper again. So then I'll. So the idea broadly is that um, you use inertial amplification is basically about using certain lever arm constrained mechanisms which do not actually increase your degrees of freedom. It's important that degrees of freedom are not increased, but but they but they you know, increase the inertia associated with the yeah mode. Awesome. So now we're at so this is the next paper. Phononic band gaps by inertial amplification. So the first paper, I think inertial amplification was hinted at, but it was not really fully used in a crystal, periodic crystal. The the the, the systems they were dealing with were still finite systems, not crystals. Right. So right. So this is the now this is the same broadly this is the same thing that we showed in lateral local resonance. However, instead of rigid link, they give it some stiffness Ka here. This is the stiffness K, and there's some theta. What they say is like if these move by u, and this moves by u by tan theta, which is again the same thing, just written in a different form. Um, and in our previous case, the Ka was infinity, so it was a rigid, absolutely rigid connection. Even in this paper, they show what happens if Ka is infinity, if it's considered rigid. They show that. Okay, interesting to note is this u by tan theta. That is the displacement, the amplified displacement. So that means if you decrease theta, tan theta will decrease. That means u by tan theta will increase. The closer you get to zero, the more it will increase. Now, at zero, I guess it probably hits the singularity. So, also the system might not be really practically realizable. That is that's something to think about. So we'll take a 5 minutes break. Yeah, so welcome back from the break. So this is the inertial amplification model that is considered, and we see the sort of similarities with the lateral local resonator. So let's see what they have done. Right. So this is the equation, the monomer. Yeah. This is the monomer equation. The monomer equation, and what we see is that there's this term, this additional term. So originally there was just m, or like in this case 2m, but now there's this additional term. So inertia has increased, and I think somewhere they must have mentioned mass ratio, dynamic mass ratio. Okay, yeah. So this is the new form, this right? Okay, so now they make a 2D lattice out of these. Say has some, these truss elements only, and at the top of the trusses everywhere you see mass Ma being placed. Right, this is that we saw here. Ma. So yeah, and using this as a unit cell, uh, you can, they've made a 2D crystal. So amazing work here. So yeah, without inertial amplification, if Ma is equal to 0, we should ideally get the monomer. Right. So this is the plot and structure of lattice for, say, yeah, Ma is 0. That implies this is not inertially amplified. Solid represents the longitudinal, and dashed represents the transverse branch. Yeah. See the stark difference. This the cutoffs are somewhere near 2.5. This is this MA is like zero point 0.5 by 6. Still not huge actually. Yeah. So the cutoffs, remember, they were at 2.5 somewhere here, and now they've come down to 0.8 or something like that. It's a huge reduction. So so the cutoff frequency has gone down, and that is what was intended with inertial amplification. And what is this omega s? Yeah, that's the frequency. So well, they've done some more detailed studies. It's totally worth looking at this paper. Uh, so this is the first proper realization, complete analytics of inertial amplification in phononic uh, crystals and 2D crystals, that too. So yeah, groundbreaking work. Uh, cool. So the idea is like this is what inertial amplification is. So okay, we have a lot Also, they have used Lagrangian formulations. I can use Lagrangian formulations. In this lecture so far, we have not used Lagrangian formulations, but you know what? We can use. You can use it. So maybe in the coming lectures somewhere, we can do one or two Lagrangian formulations, and we can plot dispersion curves based on that and see what are the rules of it, because that I feel is not covered properly. Because most people do not use Lagrangian, but when the systems become complicated, especially the 2D systems, 3D systems, Lagrangian is a nice way out. It's really helpful. So, but then there must be some way to verify it. So you can use numerics and also knowing how exactly to apply the Lagrangian, like that's also crucial. Um, okay, then we move to the next paper. So I'm really just paper hopping. So I'll show the next paper, and amazingly, even the next paper is by Yilmaz. Yilmaz has done incredible work in inertial amplification. Okay, so let us see. Okay, so this theory of phononic gaps induced by inertial amplification in finite structures. In finite structures. Uh, so earlier showed phononic gaps in infinite crystals. Right. So here inertial amplification will be covered at band gap level, which is infinite crystal, and what happens in finite structures. They are not fully covered finite structures. It's worth covering. Um, so yeah, this is the same. Not the same. Uh, that was uh, that was a parallelogram, and this unit cell is a square. However, the truss, the smaller trusses inside are the same. And then you use this unit cell to make something bigger, and you give an input from the top, and you measure the output at the bottom. Finite structure with some boundaries. Now, what happens to the band gaps? Like here you see, yeah. So here you see on the left side the plot, the first plot, it refers to it's a dispersion curve. It's a 2D dispersion curve, and we have a band gap around from something like 2 to 3. And on the right side, this is a FRF. So transmissibility is measured like output by input amplitude, sort of in decibel, like if you compare. So, so you see that there's a strong dip again here is the frequency 2 to 3. We are looking at figure 3, second panel. So yeah, if we look at figure 3, second panel, then see that there's a dip in transmissibility. So that means that although we did not cover this, but that's what typically happens is the band gap regions do not allow waves to propagate. And in those regions, you will see dip in transmissibility. Yeah, sorry, there was some network issue. Yeah. So, so yeah, wherever there is a band gap, we see that in that region there is a dip in transmissibility. So, so the finite results are sort of validated. Yeah, this is yeah. So this is a broader and lower band gap than metamaterial sort of is designed slightly different way. So see here they mentioned this is a lattice where inertial amplification dominates. And we can clearly see the effect of inertial amplification in making the band gap broader and narrower, broader and smaller, not smaller, broader and lower. Yeah. Also, they say that inertial amplification gaps are qualitatively different from the two well-known gaps in terms of wave energy localization and depth profile. So they are saying that local resonance and inertial amplification both have deep anti-resonance notches, and their gaps are qualitatively similar. So what this points to is that the question that is inertial amplification um, different from brag and local resonance, or is it the same? So what is it? It turns out it's totally different from both. In some ways it is similar to one, some ways similar to the other. And we talk about the attenuation peaks in band gap and anti-resonance notches in the FRFs. They are present in the inertial amplification band gap and the local resonance based ones, but they are absent in brag. Um, Whereas they speak about energy localization and local resonance a lot of energy propagates through the structure as local resonance are generated all over the domain. Yeah. Conversely, the energy is localized near the excitation source. So yeah, energy propagation wise, they are different. Furthermore, energy localization wise, inertial amplification is like that. Yeah, so that is interesting. Yeah, so it's an amazing conclusion. Uh, they explore energy localization, they explore this anti-resonance notches that they have explored. And their observations have hit the right spot in the first go because a lot of follow-up research just ends up validating what they are saying. Right, so inertial amplification is kind of like brag in some way, kind of like local resonance in some way, but it has the advantages of both. Think about it. And further, it is low frequency bandgap. So that is why inertial amplification is introduced at the end of all the other band gaps and all the other systems because it really hits the sweet spot. Let me stop sharing. I think this lecture has probably like gone far too long. Um, okay, so what do we observe? We observe that it has a attenuation like that of a local resonance or lateral local resonance system. Energy localization like that of brag. It's unique new type of low and broad band gaps. Jack, these are really crucial. Okay, so in the next class, before talking about the next class, let's see what we have done. Yeah, so we started with lateral local resonance, then we showed a lot of, I think we covered a lot of literature as well that's not covered in these notes. It's covered in the, as derivations, this is like very crucial in the minor points. If you get them wrong, you'll totally mess it up. We'll also learn that, these dynamical matrices, they have to be Hermitian. So yeah, and also we'll have a look at that. So basically, they are uh, the they're the same as their complex conjugate transpose. You see that everywhere. Like even here, you see. So then we highlighted the assumptions in LLR, which also happen to be its limitations. The limitations of LLR. These are advantages of inertial amplification. Yeah, so we can read these and then the next class we'll cover what we could do is, so we have two options. One is we could talk about homogenization. Since we already touched upon effective mass, effective stiffness, we could talk about homogenization because we didn't go too much into depth. But that is really fundamental because we started this course because we said metamaterials offer, like unique properties, when homogenized, such as effective, negative stiffness, negative mass. So, that has to be covered. But before we reach homogenization, I want, yeah, people to go through these notes. I'll share the notes. I want people to go through these notes, and I'll, in the next lecture, we can implement these codes in MATLAB. We can see the dispersion, we can plot the dispersion curves, and we can plot the attenuation values, and even plot the mode shapes. So yeah, so that's what we are going to do. I think MATLAB would be fun because a lot of theory has been covered. So let's just implement a few things in the code, and yeah, then play around with some values. That would be fun. Okay, see you guys.